rightly said, there will be more time with your breakout session from 4 p.m. to follow up with you and more personalized questions there. Now, I do think we've got Bruno from ULA on the line, just confirming that. Hello, Tori.
Hello.
Lovely to hear you and to have you with us. The floor is yours for your talk on the €1 trillion Cislunar Econosphere.
Excellent. Well, thank you for having me here. I have some charts. I hope that you can all see them. Excellent. All right. Whoever is driving, if we could, thank you, very good. If we could have the charts, and you do. So I did, as a kind introduction shared, want to talk with you today about how all of us can help to create an entirely new €1 trillion per year cislunar econosphere. So if you could go to the next slide, please. So just a little bit about ULA, because I also want to talk about some of the technologies that we are developing right now to help enable this. And of course, if you aren't familiar with us, we are a very experienced space launch company, perhaps the most experienced. If you have ever used GPS to get somewhere or checked the weather today to make sure it was okay for wherever you might be traveling, we have touched your lives. We have launched 142 times. We have never once failed to take our payload to space. Go to the next slide, please. This is the infrastructure that I'll be talking about in a few moments that is going to create this enabling technology. We enjoy the Western Hemisphere's largest rocket factory at over 2 million square feet. In that upper left photo, you can see a booster for the Delta IV Heavy rocket. That's one of the side cores, an Atlas in the middle, actually an Atlas on the far right, and our new VULCAN rocket in the middle. There's 4 pads on 2 coasts, a custom-designed rocket ship that can ply the mighty Mississippi as well as the open ocean to deliver these rockets to launch sites in controlled conditions. Go to the next slide, please. All right, so let's talk about the new rocket, because this is where the technology comes in. Next slide. We have retired the Delta II and the Delta IV medium, and in a handful of years, the Delta IV Heavy and the mighty Atlas V will also fly out, all being replaced by this single-core Vulcan. And in a single core, it is in fact more powerful, more capable than the majestic Delta IV Heavy. But for our conversation today, the most interesting thing is this new CENTAUR V upper stage. If you could go to the next slide, please. All right, I'll talk about this just a little bit. Today we fly the CENTAUR III. It is in fact the longest endurance, highest performance upper stage ever flown. It can operate in space for upwards of 8 hours. It can do as many as 7 burns to go to very complex destinations that you can't just simply blast from the Earth and go straight there. Some of them require quite a bit more finesse. And of course, it also delivers the most precise, accurate orbital insertions that are available anywhere in the world. So it's a great stage. But CENTAUR V takes all of this up a notch and heads us in the direction of enabling this transportation system that's part of this economy. CENTAUR V is going to have almost 3 times as much energy, which is a tremendous, tremendous amount. But more importantly, it will not operate for 8 hours. It will eventually operate for upwards of 4 and 5 months in space, which means it is also refuelable and can in fact operate indefinitely. So we really jump this up literally orders of magnitude in order to create what will become quite literally a highway through cislunar space upon which this economic activity will occur. If we could go to the next slide, please. This is the path that it will take to get there. In just a few months, we'll be flying this Vulcan single-core heavy rocket. It'll have the Mark I version of this, which has got a big increase in energy and about a 40 to 50% increase in endurance. But then we roll right ahead to our Mark II, and then finally our Mark III, which is entirely reusable in space as an upper stage. Now we're also going to be working on reusing our engines from the booster, which is an economic advantage in the cost of space launch. But this reusable upper stage is something much, much more than that. It is the foundation of what would allow this trillion-euro economy to happen. So it's really a game changer. And I love the new rocket, but I'll be honest with you guys, I'm most excited about this upper stage. Go to the next slide, please. So I wanted to give you just a couple of, sort of taste for what long endurance can do. And then we'll talk more about the economics of all of this. So this first slide is a classic trip out to the moon and back. It's something we call a translunar insertion. It's kind of like a Hohmann transfer, very similar. The important thing about it is that it's fast. It's 3 to 5 days. It's ideal for sending people back and forth through cislunar space to the moon and back. And it's a relatively straightforward thing to do. The upper stage really only needs a few hours of endurance. You give it the energy at Earth, and it goes there, and then whatever activity you're doing occurs, and you would come back. So that's what we can do with translunar. Fast, good for people. Now, if we had extreme endurance, we would also add to this in our economic activity what we show on the next slide, please. All right, so when we're doing trillions of euros of business, we will have transportation occurring all the time. There will be a continuous logistics train of materials, supplies, extracted resources coming back to Earth, heading out into this region. And what is really more important for cargo, for what we're talking about there in logistics, is the economics of it, the cost of it. And so time is not as important. So there are other types of orbits and trajectories that we can use. And this is a great example. It's something we call the weak stability boundary transfer, sometimes also called a ballistic capture. But the thing that's significant about it is you can take 30% more payload on the same rocket if you could take this different path, which is a big economic advantage when we're moving all of this cargo and material around, but it takes 4 or 5 months. And that's why the Mark II version of Centaur 5 goes right to that endurance level, and then of course Mark III goes beyond that. So that's an example of a key logistics enabler that endurance in an upper stage will allow us to have. Go to the next slide, please. All right, here's another one. I'm going to give you one more example, and then we're going to move on and talk a little bit more about economics of what's out there and how this economy grows. This is sort of a classic trip for a geo satellite that might perhaps be a telecommunications bird, perhaps an Earth observation bird when we want to look at an entire hemisphere. So we load up our satellite on Earth and we fly to a low Earth orbiting, what we call a parking orbit in LEO, so that we can coast around and get perfectly lined up with the longitude we eventually want our spacecraft to be above. Remember that in geosynchronous orbits, the orbital duration is 24 hours, so we can place it in the sky and it orbits as the Earth spins and it appears to hover there. So we typically do this with either a GTO, which is a kind of transfer orbit. We can do directly injected orbits because Centaur 3 already has this very long endurance by today's standards. And there it is, and there it stays. And so then your satellite operates until, it's very, very low on fuel, or perhaps its technology has become obsolete, and then the last bit of gas in the spacecraft is used to place it in the designated junkyard orbit, so it's out of the way and it's not, a debris hazard, and that's the end of the life of the spacecraft. Sometimes, in rare cases, there is an after-sale market where There's a little bit of life left and the technology is obsolete, but it's not out of fuel yet. And they are occasionally resold for another operator that's satisfied with that technology, but then they have to be moved. And that, again, consumes quite a bit of fuel. It takes a long time for a spacecraft to move itself because its thrust level is very low, and then it has just a little bit of life left. But that's the kind of missions we do today. We all do these. Go to the next slide, please. This is the sort of mission that is going to start happening when we place our Centaur 5 into the environment with its very long duration. We'll do that same mission I just described about, but then the Centaur 5 will go above GEO and wait until it's called upon. Days, weeks, months, even longer, and then someone will say, gosh, I would like to extend the life of my spacecraft. And we will drop down and grab it and move it to a place to be serviced, refueled, perhaps its technology upgraded, then move it somewhere to its original or perhaps new location, all in hours. For a spacecraft to move itself around to do things like that, even if it was available, again, takes weeks or months because of that level of energy and thrust. But with a stage, we do this literally in hours. And that, of course, not only extends the life and the usefulness of these birds for their original owners, but creates an entire industry around resale and reuse and servicing and maintenance of spacecraft on orbit. It's no longer a one-shot to space, use it up, throw it away. It's now an ongoing activity, much like systems that we have here on Earth. All right, go to the next slide, please. So that's just sort of a taste of that, and I'll leave it to your imagination. But what we're really talking about with these capabilities is a transportation network, a vast equivalent of a highway system through cislunar space to move goods and materials and equipment back and forth, and all possible because of that endurance. But now let's talk about why we would be doing that. And that is all about this vast new economy. So if we could go to the next slide, please. Well, it turns out that there is a tremendous wealth and abundance of materials on the moon and on what we call the near-Earth objects, asteroids, if you will, that are within easy reach of the moon. And we know this by virtue of the last decade or so of research and exploration, and now have a very good idea of how much is there, what it is. And by the way, as we continue each year, almost each month, to catalog these objects, we find more and more. So this is a growing number. But to put it in perspective, I think the easiest way to grasp it is to understand that there is well over 1,000 years worth of Earth's entire planetary production of industrial metals in these near-Earth objects alone, as well as on the moon. So just a tremendous abundance of material. In more precious metals, gold, silver, platinum, etc., than has ever been extracted in all of human history. Now, these materials that are very rare here on Earth aren't really all that rare in the solar system. They're only rare here because of the way our planet formed and where they were subsequently placed within Earth's crust and below. But actually, when we go out to these objects, which have much, much less gravity and were formed via different mechanisms than the Earth was formed, this valuable material is basically laying on the surface for all intents and purposes. And in fact, in some cases, this, a small asteroid might just be pretty much a giant hunk of platinum. And so extracting this material in these vast quantities is something that would be entirely possible and would really change the economic equation here on Earth in terms of their scarcity. So this is just a tremendous opportunity for wealth and for things that we can do for our planet that will fundamentally change the state of human dignity here. Go to the next slide, please. Now, having said all that, where's the gold rush? I mean, I've just shared with you that there's essentially gold in those hills. Well, to get to that requires this transportation network we talked about. And it's not just the technology I shared with you relative to these very long endurance stages we're developing. It's also the energy that powers them, the fuel, if you will. So just like, economic activity here on Earth that occurs across distances, it's about transportation and ultimately about energy. And here on Earth, that's primarily about petroleum when we talk about that type of economic activity. In space, we're talking about rocket fuel. And this is an economic activity across distance, far greater than anything we are accustomed to here on Earth. It's not 10,000 miles through the Suez Canal, it's 230 or 300,000 miles through cislunar space. So it's really about propellant. And the unfortunate situation that we have is that we live down inside a very, very deep gravity well here on Earth. And to lift the propellant out of that gravity well, and it takes a lot of it, because we're talking about rocket propulsion. It's not like flying an airplane where we count on our atmosphere to provide the lift that holds the airplane in the air, or a ship that is buoyant upon the ocean. Rockets fly by expelling mass, and that mass is rocket fuel. So you have to carry a lot of it out of this gravity well, and that is a tremendous economic disadvantage or inhibitor or barrier that has to be overcome to take advantage of these tremendous natural resources right here on our doorstep a week or so away. But as it turns out, the universe has provided. Rocket fuel is actually sitting on the moon right now waiting for us to use it. We would go to the next slide, please. Thanks to the exploration efforts of the Chandrayaan spacecraft and the follow-up mission that was LRO, our own Atlas flew that, where we confirmed the presence of water by crashing a Centaur 3 at over 5,000 miles per hour into the Caboose crater, throwing up regolith, flying through it and finding out, oh my gosh, there's water there. There has been continual research from that point forward, and we're now quite confident there is at least 20 billion metric tons of water on the moon. Now, water is important because people are going to be a big part of this, and people use a lot of water. But it also turns out that water is rocket fuel. It is relatively easily converted via electrolysis into liquid hydrogen and liquid oxygen, which are, in fact, the most energetic, practical rocket propellants that we use today. So literally, the best high-octane gas we could ever hope for is sitting in vast quantities on the moon and on these, by the way, on these near-Earth objects. Turns out water's pretty much everywhere we look now in the solar system. And so the propellant is already there, and we need not lift it out of the Earth. Now, I often get asked when I talk about this, well, Mr. Bruno, what's going to happen when we, use up all of the energy on the moon, just like using up non-renewable resources on the Earth? Well, first, we want to talk about how much time we'll have available to us utilizing this water on the moon. At our current demand in space, this is about 100 million years worth. Now, we're going to have this giant economy, so that demand is going to go way up. Let's say it goes up by a couple orders of magnitude. We'll still have 1 million years of rocket fuel on the moon. And by then, we'll be far beyond the moon and into the vastness of our solar system, where our resources are, for all intents and purposes, infinite. So this is not a concern near term, but what is a concern is the required infrastructure. It's great that there's ice on the moon, but ice isn't propellant. We can't just pull up our stage, pop open a hatch and throw in some ice and away we go. It has to be converted to propellant. And to be specific about it, we need an ice mine, we need a refinery, and we need distribution of that propellant. So go to the next slide, please. This is one of the typical concepts that our community that we've pulled together to work on this looks at. There are other ideas or other strategies for extraction, but this is a good, useful one for economic modeling purposes. So in the center of the chart, we have a concept that would assume that the water is in the form of particulate distributed throughout the regolith. It might be in glaciers, in these permanently shadowed craters. We don't really know yet. Exploration and prospecting, if you will, is a part of this. But this is one of the modes that it could be in. And in this mode, we sublime it, we capture it, it freezes, of course. We use electrolysis, easily powered with solar. Nuclear would also be an option, but electrolysis is an easy enough process that solar is very, very practical. And then we store it. Some of it we would retain as ice because it stores easily, and others we would retain as ready propellant, which is a little bit more challenging to keep because it wants to boil off even in the cold of space. And then, of course, depots that would be present. So that's the basis of the concept. And I show you this because I don't only have rocket scientists at ULA. I also have economists and finance folks, and we have put together a mathematical model to simulate this economy, where this is one of the inputting sort of foundational building blocks so that we can model how much over what time and what economic activity that would stimulate. And so if we go to the next slide, I'd like to show you some results. So what you're looking at here is a model where we have assumed that there has been some help getting over the initial threshold of establishing that first infrastructure of the ice mine, the ice refinery, and the depot. And so, which is another way of saying that perhaps our governments have collaborated on something that we call a strategic propellant reserve in space, much like the strategic petroleum reserves that the United States maintains here domestically to protect economic activity in the event of some natural disaster or other interruption of supply. So in this case, we've assumed that that initial infrastructure is in place. What you're seeing here in this upper left-hand corner of the slide is the size of that corresponds to the output of the economics I'm going to talk about in a moment. So what we have is a 6,800 metric ton capacity of propellant. About half of that is a strategic reserve, and the other half is additional or excess capability that is available for commercial trade. And the half that is for strategic reserve, the 3,200, is derived from about a year's worth of economic activity protection, as well as about 2 years of human transportation, which is sized specifically to deal with regular travel to and from Mars, which is about a 2-year trip. That's where that comes from. And so if these are the quantities that you put in place and then allow to run commercially, you get the output that's on the bottom. And so the horizontal axis is time, starting now and running out to 2050, which is a little bit less, as you know, than 30 years from now. That black wedge is just the propellant business, just the buying and selling of propellant in space for this activity that's occurring there. That grows to about $630 billion per year of new economic activity. But what's way more interesting is that it stimulates and makes possible all of the other economic things we talked about in the earlier slides. And that's that top wedge that grows to over $3 trillion or over 2.5 trillion euros per year within that 3-decade window. An entirely new $3 trillion economy. Go to the next slide, please.
2 minutes.
So, one of the other things we talk about often is what sorts of regulation and economic environment sort of things are required to make all this practical. And I'm not going to go through this chart with you line by line, but just to give you a feel for it, we have also taken a look at that. And as we look on the left, we can see sort of the legal framework that might be needed to do this sort of activity in space, things like real estate rights, the right to extract goods. If you have extracted them, are you allowed to own them and resell them? This is not all given. It has to be something that countries agree upon. You know, the right to be free of interference, you know, regulation and so on. And along the top, these are sort of the three major legal instruments in place: the Outer Space Treaty that's been there for quite a while, the recent U.S. Space Competitiveness Act, and of course the Luxembourg Law. And there is a basic framework here with a few gaps that we would want to fill in as we go. You know, there are provisions for extracting and owning goods and reselling them, and Luxembourg has focused quite a bit on the practical questions of who would coordinate this and how would that activity itself be funded. So that is all something that I think is understood and would be something that countries do together as a collaboration. Now, if I go to the last slide, we'll just kind of finish up with what the journey might look like. Thank you. And so this is sort of a timeline with a few benchmarks, if you will, along the way, starting from today, where there's about $400 billion of business being done in space, maybe around 6 people, if we count the International Space Station there at any one time. Though they don't really live there, you know, they're working there, and they go and work there and come home. But as we move through time, of course, we're doing these natural resource extractions, this propellant business, but we're also seeing things that are uniquely done in space, like the manufacture of ultra-pure materials that can only be made practically in microgravity, or the construction of delicate objects or structures, or things like human organ manufacturing that really do not lend themselves to being developed here on Earth, but could be done in microgravity. Of course, eventually we're routinely going to and from Mars with our exploration mission and so on. But what this really all brings us to is a post-scarcity human future, where we are not living as we are today in an environment with ever-diminishing resources, seeking how to be more efficient and live ever smaller lives, knowing that someday these things run out, but instead tapping into these literally limitless resources and allowing us not only to do that, but to grow beyond into a permanent human presence beyond this planet. And so with that, those are all the slides I have. I'm certainly available for questions if we have time, and there are any.
Hello, Tori. Hopefully you can hear me here in Luxembourg.
I can.
That was absolutely fascinating, and there have been a lot of questions online. I'm following them all. I'm also keeping a very keen eye on the time today, so I'm trying my best to keep to time. But let's just take a couple of questions then. Quite a few about Centaur 5. So if I go back up to the first start of the questions, Mark Saunter asks, what is the propellant load of Centaur 5, for instance?
Yes, so it is about 2.5 times the propellant load that we have today on Centaur 3. So we are moving from what is a slightly over 3-meter diameter tank to one that is 5.4 meters in diameter, so well over 100,000 pounds of propellant as we grow that. I'm not going to give you the exact number because we are going to be flying that pretty soon, and we're actually keeping some of the performance numbers associated with the rocket close to our vest, at least for the time being, until it is generally marketed. I would like my competitors to have to do a little bit of work, at least in the meantime, to figure out what we're up to.
Melchiorre, the chair for this afternoon, has a question for you now.
So thank you very much, Tori, for the presentation. Quite interesting. I was scrolling in the questions in the chat. I think one that caught my attention was Are the propellant construction concepts something that you plan to build, or are just concepts? And my additional question would be, are you planning to be involved in the production of the fuel, or are you just a user?
Yeah, what a great question. So, what I just described will take a big effort with lots of partners, lots of companies, lots of countries. This is kind of a whole world endeavor. And we have put together a community we call the Cislunar Marketplace that's about 200 different companies, a few universities, there's a couple of space agencies in there that share this vision, and we are all collaborating on this, and each of us has a specialized area. So we see our role at ULA as first helping to bring us all together around this, but really after that focused on the transportation network. So to get to your specific question, I don't plan to be an ice miner or a manufacturer or refiner of propellant. I do plan to be the trucking service that uses that propellant.
Thank you very much.
There are so many questions coming in for you, and also great thanks for a very, very inspiring speech. So hopefully you will be able to follow the questions as well, and you can perhaps reach out to those people, or they can reach out to you more individually, because unfortunately, due to time, I need to move on, but it really has inspired so many people, and you'll be able to see all of those questions, from very specific questions to more global economy that's about to launch upon us in the next 3 decades. So hopefully you can reach out to them and they can reach out to you.